Last week,
Present the general body meeting.
we lost one lecture, or actually two lectures. That's so bad. I will try my best to make up that one because I really do not have many lectures. So this is only a 2-credit class. So is Friday afternoon good for you guys? I really like to make up. Okay, so anyhow, that's what I thought. That's what I thought to do Friday evening, or I know you guys hate Fridays. So me too.
Oh, he's not kidding.
Anyhow, I will talk with Cynthia and see what happens. Okay, I will try my best. So, and this week, today, we will start chapter 3. This week and early next week, the first lecture next week, I'm going to finish chapter 3, which is really important. Okay, so for material science and engineering, crystal structure is a core. Okay, it's very important. And the week after next week, we're going to have the first quiz, okay? So the week after next, the Thursday after next Thursday, we're going to have the first quiz. It will be 20 minutes, cover only chapter 3, okay? So tonight, I'm going to assign homework with chapter 3, which is due 2 weeks from today. Okay, so that means when you turn in your quiz, you also need to turn in your homework. Okay, so you have 2 weeks to finish the homework. So I will let the TA to post the scan homework problems online on the e-learning. Okay, so because I know some of you guys might not have the same copy as the textbook as I have, but don't worry about that one. The TA will scan the homework problems, okay, post online. So that's kind of like the plan for the next 2 weeks. So far, any questions? Any questions for me? If not, then let's start the chapter 3, okay? So, as I mentioned, this chapter is the most important chapter in this textbook, okay? So, there's always problems associated with this chapter in the midterm, final exam, in the quizzes, especially the first quiz, okay? So pay attention to that, okay? You need to start read the chapter 3 tonight, okay? So, crystal, actually, you guys know about that one, right? Compared to the amorphous material. Amorphous means no structure, no order. Crystals have the 3-dimensional order structure, right? So as shown by this cartoon here, you can see, if we think about this as a silicon crystal, okay, which is the main materials for making the microelectronic device like computer chips. If you think about these blue atoms or the blue spheres are the silicon atoms, so you can see that they're arranged in a periodic order, right? So, and also we use these kind of rods to indicate the bonds. Okay, covalent bonds, right? For silicon atoms, they have covalent bonds in between them. So if you think about this one to be an infinitely large planet, okay, if we repeat this kind of a crystal structure later, I'm going to show you there's a smallest unit. If you repeat that one, extend that one to the 3-dimensional space, you will get this periodic structure, the crystal structure, right? So that's easy to understand. So that means we call this kind of lattice periodic structure, we call them space lattice. Okay, so you can also see that from the space lattice, the atoms are actually arranged in a long-range order. So you can imagine that when they are kind of like infinite, repeating their positions, you get a crystal, right? So, and what's important, as I mentioned in this class, what's very important is the material properties depends on their structure, right? So property and structure relationship is the core for material science and engineering. So the reason for that is because the properties of the solids could be crystals, could be amorphous materials that depend on their crystal structure. Also depend on what types of bonds and the bond force are. Okay, today I'm going to give you some example about that, okay? And as I mentioned, you can think about the lattice structure or this kind of space lattice as, you know, the atoms linked by the rods indicating the force, right? Or the bonding between the atoms. So indeed, as I mentioned, if we think about this kind of imaginary three-dimensional arrangement of atoms with the bonds, if you try to shrink them, you can always find, for the crystals, you can always find some simplest or the smallest unit. Okay, we call them unit cell. Once you repeat this unit cell in three-dimensional arrangement, you will get the final lattice space or the full three-dimensional crystal structure. Okay, so the smallest one, we could, you know, you can repeat. If you repeat that in 3D space, you get the final crystal structure. We call the simplest unit, the smallest unit, we call them a unit cell. Okay, for unit cell, there's always unit cell parameter there, okay? So 6 parameter can define a unit cell, okay? So the 3 actually indicate the length of the unit cell, which is we using the A, B, and C. Okay, later on, when we, you know, in today's class, when we talk about the Miller indices, the A length is aligned with the x-axis. X-axis actually is coming out of the plane. Okay, think about the screen here. X-axis, the positive x direction is coming out toward you. Okay, so that's, and the corresponding lattice or this kind of unit cell parameter, we call that A. Okay, this is the distance. B is parallel, directing to the right. That's a positive y direction. Okay. In the unit cell, we call this y direction unit. We call that B unit. Okay. And the vertical, which is the Z, positive Z direction, the length is C. Okay. So we have A, B, C indicate the length of this unit cell, and across from the lattice A, from this length A, there's an angle there. We call that angle alpha. Okay? So it's easy to remember, right? Because A corresponding to alpha, B, the opposite of B, the angle called beta. Opposite to the C is called gamma. Okay? So therefore, if you know the 3 lengths of the unit cell and the 3 different angles, we can define the shape of this unit cell. And then using the unit cell, if you repeat them along the x direction, positive x and the negative x, and also along the positive y and the negative y, and also positive z and negative z, you get the final structure, right? You get the crystal structure. So therefore, to define a unit cell, we need 6 parameters, okay? So you might think about, oh, there's a lot of different elements have very different, you know, many different crystal structure could be, right? How can we categorize them? Okay, how can we define all the different crystals? Indeed, after many years of study, this kind of seems like a very complex job. It's very easy to handle. Okay, not that many of the crystal lattices are available. You only need 14. Okay, so that one actually is discovered by Brevis. You know, he found you only need 14 different type of unit cells. Actually, only using 7 different types of the building block. You know, later I'm going to show you these 7 different types and also 40 different lattice space. You can get all the crystal structure being well defined. Okay, so using these 7 different type of unit cells and combined with 4 basic types of unit cell, combining them you get 14. Okay, I'm going to give you that one. So these 14 different type of unit cell can define all the crystals, okay? Let's take a look of the 7 basic type of unit cell first. The first one is a cubic one. Cubic one means what? Cubic one, if you recall this figure, cubic one means X or the A, B, and the C are equal to each other because it's a cube. The unit cell is a cube. Cube means what? X, Y, Z unit equal to each other, right? So therefore, if we think about the first type of a unit cell, it's a cubic unit cell. That means A, B, C equal to each other. The basic unit is a cube, and also alpha, beta, gamma equal to 90. Okay, it's really a vertical cube. And in this kind of the cubic unit cell, if we apply these 4 different type of basic types, you will see that not all 4, like from the simple, body-centered, face-centered, base-centered, not all 4 basic type that can be applied to this cubic unit cell. Okay, only 3 types of those are applied to the cubic unit cell because of the arrangement of the atoms. The fundamental reason why only 3, not 4, is because the arrangement of the atoms. When the atoms are too close packed, they were kind of like they will repel each other. Too much of the stress we're building inside. Okay, so when we think about the cubic unit cell, what you will find the center. So that means the 8 corners of the cube, each of that were occupied by 1 atom. We call that a simple cubic cell. Okay, easy to understand, right? So that actually takes this simple basic type off. And also you can think about the body center. So that means each corner of the cube, there's 1 atom, and also in the center of the cube, there's another one. Okay, so that's called the body-centered cube. Okay, that's a second type. Okay, we only need 14, don't forget. Okay, and also for the cubic unit cell, another possible one, we call that face-centered cube. Okay, so that means each corner has 1 atom, and on each surface, in the middle of each surface, there is another one there. Okay, so that means we call that a face-centered, because on each face of the, how many faces that a cube has? 6, right? On each of the 6 surfaces, in the center of the surface, there's another atom there. Okay, so therefore you can put the face-centered cubic unit cell there. Okay, let me ask you one question. Before we go ahead. If you think about the efficient use of the space, okay, so that means in the unit volume of the space, for these 3 types of unit cell, cubic unit cell, which one, the face-centered, or the simple one, or the body-centered, is more efficiently used in the space? Definitely face-centered, right? Because this one, later I'm going to tell you, we need to calculate, okay? In the later class of the first lecture today, we will spend a lot of time on comparing how much of the space will be occupied by the atom in these 3 very simple cubic unit cells. Okay, that's right, exactly. Face-centered cubic is very efficient, it's close packed. Okay, so that means the highest volume that can take by the atoms is, we call that FCC structure, face-centered cubic structure. This one can take 74%. Okay, this one, and how about the body-centered and the simple one? Which one is next? Is next efficiently used in the space? Definitely the body-centered, right? Later on today, you will learn this one, the atoms will occupy 6 to 8% of the volume. 74%, 6 to 8%. What do you think about that? That's about 53%. Okay, so that's very important indeed. Many of the properties of the crystals depends on if they're, highly or if they're densely packed. Okay, give you one example here. One example. Okay, if we think about the silicon, Okay, silicon, as I mentioned, is one of the most important material for making computer chips. Okay, so if the atoms of the silicon, they occupy the space in different way. For some of the silicons, they could occupy like the simple cubic structure. Okay, we know that for those kind of structures, silicon atoms will only occupy about 53% of the space. Okay, another way, we can also get a wafer, which could be more expensive. You can get FCC's crystal structure. That means 74% of the space were occupied by the silicon atoms. Okay, so indeed, for these two types of different silicon, their chemical properties are very different. Okay, if you dip the FCC structure silicon and the simple cubic silicon wafer into, say for example, an etching solution, okay, just guess which one is more reactive. So that means the etching will be faster. The less densely packed or the more densely packed one? Which? Definitely the less densely packed one, right? So that means if you compare the wafers made out of these two different silicon wafers, if you etch in, this one, the etch rate is much, much faster because you have less atoms need to be etched away. That's the reason, okay? So that means properties determined by the crystal structures, right? Okay, that's just one example. Okay, so anyhow, cubic unit cell, we have three types, right? Simple, BCC, body center cubic, and the FCC, face center cubic, okay? The only thing we do not use is a base center one, right? Take a look, okay? And then if we go to the next one is an extension of the cubic cell. So that means A and B equal to each other, but the C direction, the length is different. It could be longer, could be shorter. Okay, so A equals to B, but C does not equal to that. And all the angles alpha, beta, gamma still 90 degrees. So it's more like a cubic structure. You just extend it. Okay, easy to understand, right? Angle does not change. Just one axis is getting longer or getting shorter. Okay, we call that tetragonal one. And in the tetragonal one, if you combine with these four basic types, once again, not all the four types of basic structure can be combined with the tetragonal one. You only have two types, okay? As I mentioned, the reason for that one is because you know how the atoms are trying to repel each other, okay? They cannot be too closely or too densely packed, okay? So for the tetragonal one, you only have the simple one, simple type, so that means 8 corners atoms occupied, or by doing the body center. So that means, you know, once again, you cannot put the atom at the center or on the surface because of arrangement of the atoms, okay? So tetragonal one, you have two types, and then we can extend more, okay? To the third type, basic type is called the orthorhombic. So that means A, B, C not equal to each other. This one is more different than this one, right? So the only difference from this one is here, two of the axes, A and B equal to each other. But here, all three basic legs not equal to each other. A not equal to B, not equal to C. But all the angles are still 90 degrees. The same is for the orthorhombic one. This is the only basic type that has all four different unit cells can be combined with. Okay, so the orthorhombic has all four from the simple to the base center. Base center means the top and the bottom. In the center of the top bottom plane, you have two atoms there, okay? And also the body centered and the face centered, okay? So the orthorhombic is a very special one. You have all four different basic types. And then if you go further, so that means you have this kind of orthorhombic one, or no, it's not the orthorhombic one, the cubic unit cell. If you tilt it, if you apply a shear force along all the three different directions, what you will get the rhombohedral structure. So the A, B, and C of the length, the basic lengths, are equal to each other. But all the angles